way back. Okay, and so let's draw this in a space-time diagram. Okay, so here is Alice, and there's Alice prime, and say you have the 12 there. Okay, so let's see here. So Alice sends a light signal over to Alice prime, who then reflects it back like that. And let's suppose that Alice receives, let's say this is CT. And that's CT A prime. And this is measured meters. Okay. So let's suppose that, and this is also 45 degrees filters. Okay, so this is the situation here. So Alice just sends this light signal, goes to Alice prime, and it comes back, and the total round trip time is 12 on her clock. Can she tell how far away Alice prime is with that information? How far away is Alice prime? How far away is Alice prime? So we know the distance is 6. That's because these are 45 degree triangles. So that's 6. This is 6. And this is 6. 6 is 12. Okay, so basically it takes 12 units of time to go there and back. And so 15 units of time to go there. And so basically 60 units of distance. Okay, that's what radar range is. Okay, that's how you determine distances. Okay, like radar range, they determine where the airplane is. You send a radio wave, the radio wave goes out, hits the airplane, reflects back. You find how long it takes to get there and back, and you divide by 2, and you determine the distance of the airplane. Okay, so we need to get up over a meter stick, like 1 meter stick next to that one. Okay, so let's look. Can you see how we might be able to use this situation to synchronize the clocks as well as measuring distance? So now let me think about this. This is, I'll just want to write down the word radar range. Okay, and that's how you measure distances also, well, much more distant objects. Okay, so how do we use this for clock synchronization? This event over here, Alice's clock rate 6. What is Alice's final clock rate? 6. You should also reach 6. Okay, so from Alice and Alice prime, who are about first respect to each other, they would claim that these two events are simultaneous. If they had a light source in the middle, which sent a light signal to both of them like that, they would find those two events are simultaneous. Okay, so the way that Alice and Alice prime will use this procedure here to synchronize their clocks is Alice just sends a light signal out. It gets Alice prime, she reflects it back. She takes the total time, well, the total time is 12. She divides that total time by 2, and she says, this is 6. So, and then after the experiment is over, after she receives the light signal, she yells out to Alice prime and says, hey, when you got that light signal, your clock should have read 6. Okay, and then so Alice prime says, oh, my clock read, maybe 10 when I received that signal. So what I do is I move my clock back 4 units. Okay, and then furthermore, those clocks are synchronized. Okay, does that make sense? Are we clear about that? Okay. So one of the things about this is this is a physical process. Anything that we do in nature, anything that we're always subject to the laws of nature, and so this process of synchronizing the clock is a physical process. It uses a physical phenomenon, light, and we know something about that physical phenomenon. According to principle P2, whatever light is, it moves at a speed that's independent of the motion of the source. And in this case, both sources, both Alice and Alice prime, when she reflects it, are at rest. And so it's sort of a trivial thing, but we do know that. Also, it applies, this is an important point, this physical process, according to the principles of special relativity, principles P1 and P2, applies equally well to moving observers. A pair of observers who are moving with respect to Alice and Alice prime. Okay, so suppose we had, say, Bob and Bob prime at 2 ends of a platform like this, and this platform is moving with some CV relative to Alice and Alice prime. They can use exactly the same process. Send a light signal, Bob sends a light signal to Bob prime, it comes back, Bob divides that time by 2, the total of that time by 2, and then yells out to Bob prime, says, your clock should have read blah blah when blah blah, right? Okay, and the reason we can do that is we have principle P1. Principle P1 tells us that any pair of inertial observers, say this pair compared to this pair, moving at uniform relative velocity, are equally entitled to consider themselves to get rest. Okay, and then by principle P2, we know that if you're at rest, the speed is c independent of motion source. Okay, yeah.
The line is the multiple time, you know, and I'm going to one time to it, the one time to what? So what's moving towards the line that takes time.
That's exactly right. Okay, so let's look at that. So all of this gets interesting now when when we look at the Bob and Bob prime cross-synchronization experiment or process from the Alice and Alice prime point of view. Okay, so let's do that. Okay, and I want you to be convinced that this is valid for Bob and Bob prime to do that. So according to the principles of relativity, so we're trying to understand the nature of the universe based on these principles. And if the things that we predict based on those principles turn out to be true, then we gain some confidence that those principles might actually be a fact of the universe. If it turns out to be wrong, well then the principles are wrong. So it's very important to understand that these principles are not laws of nature. I mean, they're just guesses, right? I mean, they could be wrong. They're subject to experiment. That's very important. So but what we do in physics is we guess. We guess some certain principles or some certain equations, and then we try it out. And then we see how far we can get with those. And as I just say, so far, these principles are the most accurately, one of the most accurately measured principles in all of physics. They measure with extreme precision. Okay, so here's our situation then. So we've got Alice prime, and they're doing clock synchronization procedures and rate arranging, determining the distance, all that kind of stuff. That's happening here. And we've also got Bob and Bob prime, who are moving with some velocity v on their little platform relative to Alice and Alice prime. Okay, but from their point of view, they're equally entitled to consider themselves to be at rest. Well, let me just sort of sketch something like this. So this little dashed line here is basically Bob and Bob prime space, which is moving with that platform. Okay, and the bigger dashed line here is sort of like Alice. They call this AA prime space. Okay, so this whole space, the blackboard, is the Alice and Alice prime space for which things are at rest. And here's the Bob and Bob prime space. And Bob and Bob prime are moving in the Alice and Alice prime space. But Bob and Bob prime, they're equally entitled to consider themselves to be at rest. And they have their own space. This is the Bob and Bob prime space. And so Bob and Bob prime and their space, which is moving with them, is moving through the Alice and Alice prime space. Okay? Now, in the Bob and Bob prime space, if we were inside that space with Bob and Bob prime, those guys are equally entitled to consider themselves to be at rest. All they're doing is they're standing at two ends of the platform, and they apply this clock synchronization routine. And from their point of view, what does it look like? It looks like this. Here's Bob prime. Bob sends a light signal over to Bob prime. Bob prime reflects it back. So Bob sends a light signal over to Bob prime to get reflected back. Bob looks at the amount of time, the total amount of time passed. And what does he do? Divide by 2. He takes that total time, whatever this is, 1, 2, 3, 4, 5, 6, 7, divides that by 2, 1, 2, 3.5, and he concludes that this event, that point in space-time, is simultaneous with that event. Okay, so simultaneous in the sense of this. Okay, these two events are simultaneously happening. For me, they're happening at the same instant of time. Okay, so when I click them like this, sure there's I'm at rest with respect to the air, and it takes time for those sound waves to get to my ears, so I can hear, but it's obviously equal time. Okay, so I can hear them at the same time, and they're happening simultaneously. Okay, so these two events are then simultaneous. We'll call them, say, T and T prime. These two events are simultaneous for Bob and Bob prime. Okay, so that's important. They're simultaneous. Okay, so now the interesting question is, this is all sort of obvious. The interesting question is, what does this experiment look like? What does this procedure look like from the Alice and Alice prime point of view? Okay, Alice and Alice prime see Bob and Bob prime moving through their space. But they can still, and they see their light beams and all that stuff, so they can observe that experiment happening, or that procedure happening. Okay, so let's draw that. Okay, so there's Alice and Alice prime. We're taking the point of view now that Alice and Alice prime are at rest, so their world lines are vertical. They see Bob and Bob prime drifting to the right across their frame. So their world lines, take this point over here, Bob crosses Alice's world line, and say, at this point, Bob prime crosses Alice prime's world line. And so both of them are just drifting to the right with some velocity v. And they do this rate arranging experiment, and this clock synchronization experiment. Okay, so it happens all the time. So what does it look like? Well, let's see. So this event over here, down here, here is Bob. Bob has emitted a light signal which travels over to Bob prime. So at this point over here, Bob emits a light signal traveling towards Bob prime. So the question is, what does that light signal look like from Alice and Alice prime's point of view? I'm going to draw that light signal, yeah. 45 degrees? What? That's right. Okay, so it's time at 45 degrees. Let me try to draw this reasonably carefully. Okay, so this is 45 degrees. My principle P2. Principle P2 says that the speed of light is independent of the motion of the source of light. Bob is moving to the right, and Bob prime is moving to the right. So, you move to the right. So actually, that's right. So Bob and Bob prime actually start over here, but they're drifting to the right. And so at some point, Bob is coincident with Alice, and Bob prime is present with Alice prime, which is what's happening here. Yeah. Okay, so And at that instant, as they're crossing, as one platform is lined up to the other platform, Bob Prime starts doing this synchronization procedure. Bob sends a signal over to Bob Prime, and that light signal travels at 45 degrees, even though he is a source that is in motion. Right? So Bob is carrying a flashlight. From Alice's point of view, there's a moving source. Bob clicks on that flashlight, but even though the source is in motion, Alice is going to see that light move at the receiver's level, which is 45 degrees. He's very light. Okay? And then what happens? Then that light signal hits Bob Prime and gets reflected back. Okay? So at this point here, Bob reflects it back. So I'm going to draw a light signal going back. At what angle do I draw? See, yes, absolutely. So if Bob is doing, say, a red light, and well, it depends. So if Bob, well, suppose that Bob is just a little bit to the left of Alice, then she will see his light signal passing this way, and so the light signal, you see it approaching, so the source is approaching, and so she will see the frequency blue shifted. If Bob were just to the right of Alice when he sent it, well, then the light goes that way, doesn't see the light. Okay, so this guy here is at 45 degrees as well. Again, by principle T2. Remember, we're trying to do everything according to the principles. No, I'm okay, thanks. Okay, so we got this guy 45 as well, even though Bob Prime is in motion, doesn't matter. Okay, so this is also 45. So now what? So now what? The tick marks on Bob's world line here, measuring the time according to Bob. How do I draw these? Are these evenly spaced or not? They're evenly spaced. There may be time dilation, in fact there will be. So the tick marks on Alice's world line are close together. The tick marks on Bob's world line are further apart because there's this time dilation. But that's not relevant here. What's relevant is that the spacing is even, whatever it is. Okay, so now what happens? What does Bob do? What's the next step in his clock synchronization procedure? That's right, so he counts the total time divided by 2. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11. Okay, let's suppose there's 10. 10 divided by 2 is 5. So we've got 10 there. He divides that by 2 and he gets 5. So where's the midpoint of this? The midpoint of this is about there. Okay, so that's 5. Okay, so what he concludes is that that's this one here, the event T. And so what he concludes is that this event here, halfway in between, is simultaneous with this event. That's where Bob Prime received that light signal. So he concludes, so Bob Prime would say that these two events are simultaneous. So for them, if we were to catch up with them and stand in their reference frame, at respect to Bob Prime, those two events are simultaneous this way. Like, we would hear them at the same time if they were like snapping finger events. Okay? So are they simultaneous for Alice and Alice Prime? So which one occurs first? So here's time point Alice. Here's 1 second, here's 2 seconds, here's 3 seconds, here's 4 seconds, here's 5 seconds. T occurs first, then there's 6 seconds, and then 7 seconds. Oh, T prime occurs. So T occurs at 5 seconds, T prime occurs at 7 seconds. Okay, so for Bob and Bob Prime, those two events are like this. For Alice and Alice Prime, you see Bob and Bob Prime drifting like this. They see this event, then this event. Okay, so that's really, really important. That this idea of simultaneity, when two things are simultaneous, that depends upon the observer. For me, these are simultaneous. If you're moving relative to me, you will see one first, then the other. Yeah.
Well, by the principle, because it depends on the motion of the source to light rays on, right? So in their diagrams, we have the other signal going on 45 degrees off. And then the Alice's world line is very close to the angle, and the Alice's world line is bottom world line because of the other things like that. Because of the velocity. Yeah. So there's some velocity here. Exactly. So then, when she, like, by that diagram, it doesn't make it proceeding like HCS.
Well, she is because it's not like that. So this is vertical. This is supposed to be at 45. This is on 45. So I mean, when I say 45, it goes to the blackboard. It goes to the vertical and horizontal to the blackboard. Okay, so that's that. Okay, so actually this idea that simultaneity might not be relative, may not be absolute, but might be relative, or depend upon the observer, was first suggested by Poincaré, and then a little while later it was Einstein who actually understood concretely what this means. Okay, so what this means is quite radical. Okay, it's quite beautiful, the consequences of this. Alright, so let's look at this just quickly. And then we'll take a break. Okay, so let's talk a little bit about Bob's x-axis. Okay, so we know all about Bob's time axis, right? So in these pictures that we're drawing, that's Bob's time axis, that's Bob's time axis.